Okay, so welcome back, everybody. It's my pleasure to introduce our first speaker of the fall semester, Randy Lewis. Randy comes to us from York University, where he has been professor of physics since 2008. Is that roughly right? Randy is a leading figure in the field of lattice gauge theory. He's done a wide variety of important work in a lot of different topics: tetraquark physics, beyond the standard model physics, flavor physics, and many others. But he's here today because in the last few years, he's developed a program and done some very interesting work in the new field of applications of quantum simulations to high energy physics. This is a brand new field. Only the very first steps have been taken, but it shows a lot of promise, and we're pretty excited in the high energy group about the possibilities that this might offer. So today, Randy's going to tell us about some of his work on this, implementing quarks and gauge fields on noisy quantum computers. Thanks.
Thank you very much. And thanks for having me here. It's been a fantastic day already. I look forward to the rest of it. This is very loud. Maybe I should remove this someplace below. Is that how it works? Is it going to work here? Sounds okay? All right. We will experimentally move it around as necessary. Let me know if something doesn't appear to be working. Okay. So as I was saying, this is a wonderful place for me to visit. I really have enjoyed the morning, and I look forward to seeing the rest of you during the day. My topic, as you can see from the title, implementing quarks and gauge fields on noisy quantum computers. So the plan is to have the discussion in 4 parts. The first part is, why would you want to do this? Why should we study quarks and gauge fields on quantum computers? And then I want to move on to 3 topics that I've had a part in recently, and you see them here, number 2, 3, and 4. Maybe I should say number 2 is some research I've been doing with people at the Institute for Quantum Computing at the University of Waterloo. Perhaps you know Christine Mushik. Her name is there in the list. He is a professor at that institute and leading an excellent team. I've had the chance to work with them in the past couple of years. You see the same team listed in number 4 as well. This is a great opportunity for me to partner with some people doing quantum information science and see what we can do in applying that to lattice gauge theory. And number 3 is in the center. This is a project that I did at my own institution, York University, with 3 students. Sarmed A. Rahman is the first name there. He's a master's student. Emmanuel Mendicelli just finished his PhD a week or 2 ago. He's moving on to a postdoctoral position at the University of Liverpool. And Sarah Powell finished her undergraduate degree, and she's moving to the University of Washington for grad school. So let's get started with the motivation. If any questions come up along the way, please feel free to jump right in and let me know what's on your mind. By the way, I have to click a button here. Here we go. So for motivation, we should remember that the physics of quarks can be difficult because you can't get one in isolation. Quarks are trapped inside the protons and neutrons of our world and other hadrons of our world. So, for example, if you want to think about what happens at the Large Hadron Collider, you would have a proton coming in from the left and a proton coming in from the right, and they would collide. Each proton is drawn here as if it contained 3 quarks, 2 up quarks and 1 down quark. But you and I know that what's inside a proton is far more complicated than that. There are many, many quarks and many, many anti-quarks, and gluons or gauge fields holding them together, gluons and gauge fields interacting with other gluons and gauge fields. Just inside one proton all by itself is a very complicated place. But now you imagine 2 of them are colliding. Something happens. For example, in the picture shown here, in the center of the picture, you see that a doubly charmed baryon has been created by the collision. There were no charmed quarks in our initial state. or at least none in the valence sector of the two protons, but now two have been created. An anti-charm quark has been created. There must have been another anti-charm quark as well. It's not shown in the picture. Maybe it has decayed by a weak interaction into a lighter quark. So all of this physics is something that we would like to be able to understand, but it's non-perturbative, it's non-abelian, and a convenient way to handle this physics is by computer simulation. You have a big computer, then you can handle physics like this. And there's a technique that's been in place for a long, long time. It is very, very effective, called lattice gauge theory. You have experts right here at this institution who are world leaders in lattice gauge theory. For the purposes of this talk today, let's just mention one slide as a little reminder of this field. The picture on the left shows in blue something that represents the proton. You can see the many quarks and antiquarks gauge fields inside the proton. And if you wanted to do a numerical study of just one proton sitting there, maybe you would build a giant lattice or a grid, and it would be big enough that it contains the entire proton and some of the environment around the proton. And it would be finely enough space that you have many, many sampling sites inside the proton where you could see what all the quark fields and gluon fields or gauge fields are doing, because this is going to be a quantum field theory calculation. And so if you zoom in on one of these little plaquettes or little squares in the picture, this is what you see. There are quark and antiquark fields at the nodes. There are gauge fields connecting one node with another one. And your job with your computer is to do a Monte Carlo integration. We're integrating over all the quark fields at every site, all the antiquark fields at every site, all the gauge fields represented by these capital U's. You're integrating over all of these things. And what is it that you're integrating? Well, you need some operator that will create the proton at a certain location y in space-time. And you need another operator that will annihilate the proton at some other point x in space-time. And then your integral will be weighted by the exponential of minus s, where s is the action. And here it is written as a four-dimensional integral over something that looks like a Dirac quark with a certain mass m and a kinetic term so that it can move around. And inside this kinetic term, this capital D is a covariant derivative because there are gauge fields present in that interaction with the quark. You also have a field strength tensor, F mu nu. This is where the gluons or gauge fields interact with each other and our kinetic term. And so if I think about all the pieces that we see on this slide and all the pieces that are hiding inside the notation, in some ways, it's a complex topic to think about, but it's a solved problem. Lattice gauge theory has been working very well for many, many years, decades, and is a crucially important part of particle physics and nuclear physics today. Let me just give you one example of something that traditional lattice gauge theory has accomplished. None of this has anything to do with qubits or quantum computers today. But here, if you look at what is shown on the right, this is determining what is the mass of the strange quark. Now, if you wanted to determine the mass of the strange quark, maybe what you would do is you would take a hadron that contains a strange quark. You would measure some property, maybe the mass of that hadron, and then you would infer from that what is the mass of the strange quark inside. But to make that inference, you have to understand how to calculate the connection between the mass of the hadron and the mass of an individual quark. And that's where lattice gauge theory comes in, or some other method. And so in the past, people would use some phenomenological approach and determine that the mass of the strange quark is around 100 MeV. But here in the top two panels, you'll see lattice gauge theory determinations of the strange quark mass. Many different groups. These are acronyms for lattice groups working all around the world. And you see the dates, 2009, 2010, 2012, all the way up to 2018. Different people, for different groups of people, calculating the mass of the strange quark. And the error bars are small enough that you can start to talk about the distinction between the lattice calculations labeled 2 plus 1. And this other set of lattice calculations labeled 2 plus 1 plus 1. What is that difference? Well, 2 plus 1 means that in the lattice calculation, up quarks, down quarks, and strange quarks were included. But 2 plus 1 plus 1 means you have all of those quarks plus the charm quark as well. It's there in the background of your calculation. Now, the charm quark is really very heavy. Having such an extra heavy quark nearby shouldn't make much difference when you're determining the mass of the strange quark. But it doesn't make it zero difference. And this is the precision that traditional lattice gauge theory has arrived at, that you can start measuring and discussing how important that little effect is of whether a charm quark was present or absent in this calculation. So if lattice gauge theory is a wonderfully successful tool, then why would I want to use a quantum computer for lattice gauge theory? This seems to be something that's already working extremely well. To talk about that question, we should remember that the picture we've been drawing of a lattice is actually a four-dimensional lattice. It has a length and a width and a height and an extent in the time direction. Or more precisely, in the imaginary time direction. Because the way people do calculations in lattice gauge theory is they'll perform a Wick rotation. So instead of integrating along the real time axis, imagine you're in the complex plane, you can do an integral along the imaginary time direction instead. And just with some simple math, it's equivalent. And it's a very important approach because then the Monte Carlo integral that we were mentioning before is well behaved. Because this exponential e to the minus s has an s which is positive definite. And that's what you want for your Monte Carlo approach to be practical. And that's how traditional lattice gauge theory works. But suppose you wanted to ask a different question. Suppose you wanted to measure something that actually depended on time. You wanted to watch a collision happen in real time. Or maybe you want to calculate something not where your proton is sitting in a vacuum, but you want your proton to be in an environment. Maybe it's a neutron you're studying and it's in a neutron star. Or maybe you want to study the quark gluon plasma. These are two big categories of questions, calculating in real time or calculating with the chemical potential, for which capital S is not positive definite. And in that case, the Monte Carlo approach that has been so successful is not the approach that you're going to need to use. An alternative would be to use a Hamiltonian approach to this quantum field theory. You would have a big Hamiltonian, which would be acting on a state vector, but the state vector is going to be enormous. In the Monte Carlo approach, we didn't have to store the state vector. But now you will have to store the state vector, and it's so huge, maybe this is where we need a quantum computer. You can store the state vector on a register of qubits and write your Hamiltonian in terms of qubit operators and do this Hamiltonian calculation that you'd like to do using qubits. It opens a vast new arena for lattice gauge theory of the future, questions that can't be addressed with the approach used now. So that's the motivation. And now I'd like to move on to the next part of the talk. If you do have any questions, feel free to jump in. Yeah.
So the great
right. You're creating an ensemble of possibilities, and then you're doing statistics on that ensemble that you created. Exactly. All right, let's move on to the next part. And if any questions come to mind, don't hesitate to jump in. So for this next little section of our discussion, I'd like to tell you about a first attempt to use tiny quantum computers that are available today and try to do a calculation. maybe in my dreams, I would show you a big lattice like the one on the left here, but that's not what we're going to be doing today. Let's make some very severe simplifications so that we can take our first step. You see my lists of bullet points at the bottom. Instead of a three-dimensional lattice in space, we'll just use a one-dimensional lattice. Think of one line across that grid. That will be the entire lattice of my conversation. Real quantum chromodynamics, strong force, has three colors, red, green, and blue, inside your proton. That's the strong force. Let's keep it simple and have only two. You could even have one, but then the theory would be abelian rather than non-abelian. We would like to have a non-abelian theory where the gauge fields interact with other gauge fields, as opposed to the photon, for example, which doesn't interact with other photons because they're not electrically charged. We'll also use staggered quarks. This is one of the quark options that is used in traditional lattice gauge theory as well. It simply means that on each lattice site, we won't have both quarks and antiquarks. We will have one or the other. And so if you look at my picture of the lattice, here's one site which has only antiquarks, shown as striped circles. The next site has only quarks, solid circles, and then striped quarks, and then quarks, antiquarks, quarks across the lattice. That's the staggered approach. And finally, we'll have open boundary conditions, which means over here on the left, all the fields are zero, and over to the right of the lattice also, all the fields are zero. Yes. Great question. Let me answer that on the next slide. Question is, what motivates the choice of boundary conditions? And we'll see right away how this is a really advantageous choice for us to have open boundary conditions. Yes. Good. Yeah. In the same way that in electromagnetism, your electron is charged, here our quarks are charged. And there are two kinds of charge. There's red and there's green. So the quarks are charged and the gauge fields are also charged. They will have, say, a red and an anti-green. So when one gauge field touches your red quark, it could turn it into a green quark. Yes. In real QCD, this is the name people use. It's not literal color, of course, but people discuss QCD as having red, green, and blue. And here I will only discuss two colors in my little toy theory. So let's talk in a little more detail and get back to both of these questions right now. How do we imagine mapping this onto qubits? What is this physics and how do I map it onto qubits? Here's the plan. On the first lattice site, way over here on the left of the lattice, let's use one qubit to say whether we do or do not have anti-red present. These will be the two basis states of qubit number one. Let's use qubit number two to say whether we do or do not have anti-green present. Now, of course, in general, at this lattice site, we'll have some superposition of anti-red and anti-green. It may be a totally empty site. We may have both anti-red and anti-green, some combination of the four basis states discussed by those two qubits. Notice that we can never have a double amount of anti-red because that wouldn't obey Fermi statistics. If we have two identical fermions, the wave function will have to be antisymmetric. And so we have enough qubits with just two to describe that state of the first site of our lattice. And then we'll have qubits number 3 and number 4 for the second site on our lattice to say whether we do or don't have red and we do or don't have green, and so on all across the lattice. So I know how to count the number of qubits we need for the quarks, but what about the gauge fields? There are gauge fields connecting one site on the lattice to the next. So these little horizontal black lines, these are the gauge fields. How many qubits do we need to represent that physics? And the answer is usually a lot, because the gauge fields are a continuous degree of freedom. Any finite number of qubits is a truncation of what we truly would want. But this is back to the question of the boundary conditions. We can make use of the fact that this is a gauge theory to do something that's a bit clever, at least in this one-dimensional lattice. Let's, for example, go to site number 2, this site on the lattice, and let's do a local gauge transformation at this site. It won't affect physics because it's a gauge symmetry. So we can make any choice we want. Let's make the choice such that this gauge link that touches my site on the left becomes the identity matrix. If I make that choice, then I don't need any qubits for that gauge link on the left. It's just the identity matrix. But of course, the same gauge transformation that we chose will alter these quark fields at the site. And it will also alter the gauge field pointing out to the right. Presumably, they will become more complicated. That's the price we pay for no longer needing qubits for this gauge link on the left. But of course, now we can do it again. Let's go to the neighboring site and do just the right gauge transformation here so that the gauge field on its left becomes the identity matrix. And the other fields become more complicated. And we'll keep doing this all the way across the lattice. By the time we get to the end, we won't need any qubits for any of the gauge fields. It's not that we are omitting that physics. It's that all the representations of the quark degrees of freedom have become more complicated. That physics is now inside the description of the Hamiltonian for the quark. And the description of the gauge fields doesn't need its own explicit quark. This only worked because we chose open boundary conditions. And so that was part of the reason to make that choice. Yes.
Yeah.
Great. Let me show you the next slide, which I think will make more clear what I was trying to say in words. Here is the Hamiltonian that we arrive at. It's not perhaps as scary as it looks at first glance. Don't memorize it, but let me make an important point for you. The Hamiltonian in the top line has 3 kinds of terms. First kind of term is the mass term for the quarks. And that's shown here in the line below. It is the summation over every site on the lattice. There's an effect of having a mass at every site on the lattice. The second term is the kinetic term. You might think of this as the hopping term. It means that we sum over all the sites on the lattice. You can have your quark disappear from one quark site and appear at a neighboring quark site. We can have the anti-quark disappear from one site and appear at the neighboring quark site. And finally, we have this third category, which is the interaction term. It's labeled H electric, but it should really be color electric. It's this non-abelian version of the fourth. And notice that it has terms that are double sum. These are the terms that arrived because we did this gauge transformation. We don't have explicit qubits for the gauge fields, but we have all-to-all interaction. Any pair of sites interacts, has an interaction joining them because we integrated out all these gauge fields all the way along the line. So this is the price we pay, a non-local big Hamiltonian. Yes, good. This parameter named X appears in every term except the gauge field term. So X is like the inverse of the coupling constant. When X gets big, the coupling constant, the strength of your strong force gets weak. Yeah. Yeah. Can you explain what you mean?
So whether
Okay, so what I haven't shown you here is where this Hamiltonian came from, but we're simply writing down the textbook definition of QCD, strong force, which is a local interaction, a local Hamiltonian, and then translating it into qubits directly. So this is the original theory, the true theory that we want to study. We haven't made choices, if that's what you're wondering.
So more that's okay with how does we agree to the or
How does the vacuum energy scale?
Yeah. So for me, it's not clear, looking the data and
Right. Right, right. This is something I cannot show you today because we only have small lattices, but I can show you what we have. Yes, right. Theory is absolutely a local theory. Right. Right. The local interaction would just be, imagine I have a quark at one site and an anti-quark at a neighboring site. We would then have this one gauge link, which would still be present in the theory and would join those two sites. And that would be our interaction. Well, that's the question. Yes. How could, if we wanted to keep the gauge interaction as an explicit field in our calculation, then how will we represent it in the state vector? And that will determine how we would write down qubit gates. Here you see Pauli Zs and Pauli raising and lowering operators acting on a state vector that only represents quarks. But we would need to define how the gauge fields appear in the state vector. And then we'd have some Pauli operators that act on those degrees of freedom. Sorry? You could choose the Coulomb gauge. This is not the Coulomb gauge, but this is an option you could choose. To answer the question about the gauge fields, if we go a few more slides, I will show you an example where we do keep gauge fields, and maybe it will become more clear. Great questions. Please keep them coming. Let me show you some practical results. This is a very busy slide, but I can lead you through it panel by panel. If we start in the center, here's this little square with a panel labeled D. This is a little circuit for the quantum computer. We ran it on IBM quantum hardware, and it has 3 qubits. You see the 3 horizontal lines telling me there are 3 qubits, and then you see gates. There's a gate with some angle θ1. There's another control gate where the bottom qubit controls the center qubit. It's a rotation by an angle of minus θ1, and there's another one for θ2 and a couple of Pauli X gates. This tiny little circuit is a variational circuit where you can vary the 2 angles, θ1 and θ2, and find the ground state for your lattice. It's a small lattice. Here's the picture of the lattice. It has anti-red, anti-green, red, and green. That's all. When you vary the parameters and find the ground state, you can make it the graph of the ground state, and here it is in open circles. You see it's coming down from 0. The ground state is 0 when x, this is the parameter in the Hamiltonian, the inverse of the strong coupling. It's 0 when x vanishes, and it comes down from 0 as x grows. Once you have the ground state, you could then build a different circuit, shown up here in the top right, which finds the minimum energy that is orthogonal to that ground state. So it finds the first excited state in this sector of the theory. And the way to do that, we've again shown a 3-qubit calculation. You use θ1v and θ2v as input. Those are the angles you found for the ground state. And now you have new variational parameters, θ1 and θ2, that you vary to find the minimum energy that's orthogonal to the ground state. And you put those on the graph, and they're the triangles here. So in physics, our ground state is the vacuum of our quantum field theory. And the first excited state, which is the triangles, that is one meson sitting there at rest on your lattice. And so the energy difference between the triangles and circles is the mass of this hadron, the mass of the meson. And here it is as its own plot. This is the energy difference, just calculating, subtracting the circles from the triangles gives you this graph. Now you might ask, in what units am I calculating the mass as a function of the coupling? Let's not worry about the units right now. It was just convenient units for our calculation. We'll come back to a physics question in 2 slides. So just let me calculate in my favorite units for the moment. Yeah, this is on a tiny little quantum computer where we use 3 of the qubits. Yeah. You could calculate the mass of some other particle in this theory, for example, the baryon. And we did that. In this case, you see the lattice was a little bit longer in the example I'm showing you. And our circuit is shown in perspective. So if you look over here to the right, you see, sorry, this is the left, isn't it? If you look over here to the left, you see 7 open circles. This is the layout of the actual quantum computer that we were using, had 7 qubits connected in this way. We used 6 of them for our circuit. And you can see just schematically what our circuit looked like. Yeah. Yeah, exactly. It looks as though we should need 8 qubits because I count these circles on the picture and there are 8 of them. We've done some work to only put onto the quantum computer what we really had to put on. Imagine you have a variational principle and you can write down a circuit and then you notice that your circuit can be divided into a static piece and a dynamic piece. And maybe you only need to put the dynamic changing piece on the quantum computer. So that's what we did. Yeah. So I'm skipping a bunch of details and you're catching me, and that's perfect. So just to wrap up this section of our discussion, let's try to bring it back to the physics. We calculated the mass of a meson, where the valence particles are 1 quark and 1 antiquark. And now we've calculated the mass of a baryon, which in real life is like 2 ups and a down, like 3 quarks. But in my little test example, which has only 2 colors, a baryon actually has only 2 quarks, not 3 quarks. So you might expect that the mass of the meson and the mass of the baryon are basically the same. They both have 2 valence particles. And that's true. And in fact, in this theory, there's an exact symmetry that says the meson mass and the baryon mass have to be identical to each other in the continuum limit, but not in this lattice formulation. Only as the lattice spacing shrinks to 0 should the 2 have exactly the same mass. So this is a fun little test we can do to see if things are working the way we're calculating. Here's a graph where the vertical axis shows the ratio of the meson mass to the baryon mass on our lattice. Now you can see our lattices are really, really tiny. I cannot properly take a continuum limit. I would need to have a huge, much bigger lattice to be confident, but we can at least do a test, a consistency check. What we should find is that as X gets large, this ratio should approach 1, and it passes that. That's all we can say. And notice, this is where we can come back to the question of what units are your masses in. This is my physics plot. It's a ratio, so I don't care what units my masses are in. My convenient units cancel the limit. So that was part 2 of the talk. I'm ready to move on to part 3, where we can talk a little bit about the gauge fields themselves and putting them on qubits. Unless you have any questions, I want to jump in. So this is a project I was doing with 3 students at York University, as I mentioned. And back to the big perspective, far, far in the future, I'll show you something, hopefully, with all of these sites on a lattice. But for now, we'll just look at one little chain across the lattice of individual plaquettes, square. It's not a one-dimensional line, but it's a single-dimensional row of plaquettes. The simplification is just one row of plaquettes, no quarks or antiquarks at all. That might sound like a very boring theory, but remember the gauge fields interact with each other. The gauge fields themselves carry the color charge. So this is an interaction theory. And we'll have again only 2 colors rather than 3. And now we're going to need 4 qubits to represent the color state. How much color charge do I have on that little line segment? I'll need qubits to describe how many color, what's the color charge on this line segment. Let's make the smallest non-trivial choice 1 qubit. Either there's no color or there's the minimum quantum of color for each link on the ladder. That'll be our starting point. So you can write down the Hamiltonian for this theory. And this is how it's typically written. The sum of 2 kinds of terms. There are the color electric terms and the color magnetic terms. The color electric terms describe how much color you have on each link. And the color magnetic terms are like a curl. They go around and around the color. So in the past example, which was truly a one-dimensional lattice, you remember we only had color electric terms. Now we have color magnetic terms because we have this second dimension. And you can write, I've shown here, the Hamiltonian in terms of Pauli X's and Pauli Z's. We thought it would be interesting to calculate how the system evolves through time, because that's something we can't do with the conventional lattice approach, which uses imaginary time. So the idea is to take a very small lattice, just 2 plaquettes, one beside the other, and our initial state will be that there's color charge here on the left, but no color charge on the right. And watch how that changes as time goes on. So we need to write down the time evolution operator. Here it is. And I'm skipping all the details and just showing you what the circuit looks like for one tiny little time step of this system. It's a 2-qubit calculation. We'll need 1 qubit to say whether the left is on or off. And we'll need 1 qubit to say whether the right is on or off. 2 qubits in total. And you see some controlled NOT gates and some Y rotations and Z rotations. The rotations depend on your time step. And they depend in some cases on X, the strength of your strong interaction, which is a parameter in the Hamiltonian, as you remember. And we've also ordered the pieces inside this time step in such a way that at the extreme left of the time step is a controlled NOT gate. And at the extreme right of the time step is a controlled NOT gate. We did that on purpose because if you have 2 or 3 or 4 time steps back to back, then you'll have these 2 C-NOT gates right beside each other and they'll cancel away. That's nice because the C-NOT gates are the noisiest gates on these quantum computers, and you want as few of them as possible. Yes. Oh, sorry. Yes, you do win in this case by going to second order Schroeder. Yes. 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 In this case, it is. It's a case by case path for your each Hamiltonian. Yes. So let me show you what happened when we put this on one of the little IBM quantum computers. Here's a graph where the curves are the exact result. The red curve is the probability that there is color flux in the left plaquette of your lattice, and blue is the probability that there is color flux in the right plaquette. Notice that red starts at 1 and blue starts at 0 because that was our chosen initial state. And as a function of time, they just oscillate in the pattern shown. The data points here are what we found by running on the actual quantum hardware. So you see that at early times, it works quite well. The data points are near the curves, and then they end up somewhere near the middle of the graph, where probability is a half, which means it's a coin flip. There's no information left. Is the left qubit with or without, is the left plaquette with or without color? We don't know, just flip a coin. But this is before mitigating the errors on the quantum computer. Suppose you understood the errors and could mitigate those errors, then you might see something like this, where the top panel is exactly what we were just looking at. And the bottom panel is the same data, but the errors have been mitigated. And suddenly you see a very long time extent where the output from the quantum computer matches, not perfectly, but reasonably, the true result. So what's going on here? How do you get from the top panel to the bottom panel? That's what I need to tell you. Yes. So the question is, how were the curves created? Yeah, I did that on my laptop. Yeah, that's right. This is a very small system. So certainly everything I show you today can be done very easily on a laptop. We're just trying to see what today's quantum computers are capable of. Can they? Yeah, perfect, thanks. Anything else? All right. So let's go ahead to the next step. And what I need to explain to you is what did we do to go from the top panel to the bottom panel? So to make this curve, imagine for the sake of argument that on the last slide, you wanted to make that data point that had 10 steps forward in time, and then you wanted to calculate the answer. So we had 10 of those Trotter steps, and we know what the circuit is. Another thing you could calculate if you wanted to is you could go 5 steps forward in time, and then go 5 steps backward in time. Of course, after those 10 steps, you know the right answer. You're at the initial state again. You went 5 steps forward, and then you undid them by going 5 steps back. If you run that on the quantum computer, you will not get the initial state because a bunch of errors happen. But since you know the right answer, suddenly now you know exactly what errors have been made by your quantum computer. You've measured the error. And if your circuit, where you took 5 steps forward and then 5 steps backward, has the same gates on the same qubits for the same hardware in the same order, all you did is change a plus sign to a minus sign in half of your steps. Maybe this is a really valuable way to determine what the errors would be if you then did 10 steps all forward in time. This is an answer you, in principle, don't know. Of course, you do today because we're running on a small system. But you could actually predict that result and mitigate the errors by saying the errors should be the same as if we went forward and then backward to a state that we know. And so that's what we've done here on this graph. We've gone some number of steps forward and then backwards again, and we're measuring the initial state. If the hardware was perfect, all those red points would be at the top of the graph, probability 1, initial state. All the blue points would be at the bottom of the graph, probability 0. And you see this envelope function as the errors smoothly, more or less, move us toward probability 1/2. And so this squishing down toward the center of the graph is presumably what was happening back here in the top panel. And now that you think about it, you see it, right? In the curve, look at these points. The red points, even way out here, are still above 1/2 when the true curve is above 1/2. And they're still below 1/2 when the true curve is below 1/2. The signal is there. It was just squished down in, and we should rescale by the measurement of the errors by running forward in time and then back. And so that's the plan, and it worked really well, as you can see. An important feature that was used in this self-mitigation, where the circuit mitigates itself in a sense, is that the noisiest gates are the C0 gates. You might worry that in your particular circuit, the C0 gates have a certain biased initial state when they arrive at in your circuit, and you don't want this. You want randomized errors. You don't want something special happening in your circuit. Each of these 16 little circuit bits would do exactly the same thing on a perfect quantum computer. So you should run your circuit many times, randomly choosing which one of these you put in the circuit, and this will randomize the errors and make your mitigation work much more effectively. So this was done, and I encourage you to read this very nice paper at the bottom, which was the inspiration for our use of this also. You could do it with a larger circuit, and we did. So you look at the top, here's our initial state. We have 5 plaquettes now. The center one is the only one that has color flux in the beginning. where does that color flux go as a function of time? It will move out toward the edges of our lattice. You can see the time step is a lot bigger now, but you can still run this code, and we did. And here's an example of results. In this case, the black curve says, what's the probability that the center plaquette has color flux? And then as you move out, you see the blue and the red. And you can see that each color takes its turn being the largest on the ground. As the time evolution of this system happens. It's fun for me to see time evolution because it's not something I'm used to being able to do with lattice gauge theory. And I'll just mention in passing, there are many valuable ways to do mitigation, and it's often nice to combine several methods so that you can maximally mitigate the errors in your quantum circuit. We have just a few minutes left, and that's all we'll need for the final part of this discussion. It would be nice to move to 3 color. It feels like I live in a world of QCD, which has 3 different charges, red, green, and blue. I'd like to do that on a quantum computer as well. And so with the Waterloo group, and also with Sieglinde, who is an IBM employee in Germany, we did this work, and it's not quite in the journal yet, but it's accepted. It's just interest. So you can imagine how this will go. We're back to a one-dimensional lattice now, a literal line, but we're going to have, as people were anticipating already in the questions, anti-red, anti-green, and anti-blue, and then red, and then green, and then blue, and then so on, staggered across your line. I'll show you results just from this first elementary cell. So it'll just be 6 qubits maximum. What physics would you expect to see coming out of this? And again, we're going to use time evolution, and we're going to use this self-mitigation tool to see what we can get out of it. But what is the physics you expect? Let's talk about the system where you always have equal numbers of quarks and antiquarks. Just for example, one option would be you have 0 quarks and 0 antiquarks, and you would call that the bare vacuum of your group. Or you could have exactly 1 quark and 1 antiquark. And if they come equally weighted, red, anti-red, green, anti-green, blue, anti-blue, that's a color singlet. That's the meson. Or you could have pairs of colors with their anticolors. You might call that the tetra quark because there are 4 objects in each state. And finally, you could have them all turned on. That looks like a complete baryon with 3 colors and a complete antibaryon, 3 anticolors. So we'll have these 4 energy levels that should mix with each other, depending on our initial state as we see time evolve. And here's the result. The curve on the right, this is the result of running on IBM quantum computers. And what you notice is an oscillation from time equals 0, which is in the center. You see some frequency of oscillation, and you could easily fit that frequency, which tells you the energy gap between 2 states of the system. Our initial state right there, time 0, is the one that has 6 particles inside. We just chose to start with baryonium, 1 baryon, 1 antibaryon. And you see it oscillating into its neighboring state. And by fitting that frequency, you get this gap between the baryonium and the tetra quark. Of course, this numerical size of this gap depends on the input parameters. There are 2 in our Hamiltonian. One is the mass of the quark, and the other one is the strength of the strong force. Suppose we change the mass of the quark to some other number, then you get some other result. And when we ran on the quantum computer, you see now some frequency. It's a different number than it was before, but you also see this envelope function, like a second frequency. You can fit 2 frequencies to these results. And so you get these 2 energy gaps in your theory from the original time equals 0, bottomonium. It now couples 2 different states that happen to be dominated by the tetra quark. So I'll just wrap up by saying, hiding inside those results I showed you was mitigation of errors because the hardware is noisy. If I had not mitigated the errors, you would have been looking at the blue data points. So you see there's quite a dramatic change by applying self-mitigation. It's the same mitigation method we had used before. And we're not the only people to be looking at recolor QCD on quantum computers. Here are a couple of other papers you could look at if you're interested in seeing what other groups have been doing. And it's a very active field. Many, many people are working on very important things in this context. So my conclusion is very simple. Quantum computers hold this promise of maybe new arenas in lattice gauge theories, such as evolution in real time, as we've been talking about. Initial studies have been done on the computers that are available, quantum computers that are available today. And there are mitigation methods for errors that are, in many cases, simple to implement and really, really valuable, like order of magnitude improvement in how far you can get in time extent. Thanks very much for your time. That's all I have. And maybe you have questions for me.
For that nice talk. Questions for the audience? Yeah. Okay, so the question for folks on Zoom is, how good of a quantum computer do you need before it's useful?
I guess it depends what we mean by useful. But it has. Useful in the sense that it would replace your woes with capacity. Right. So this is a really valuable point. Probably the goal here is not to replace the classical supercomputer, but rather to do physics in these new directions, like having finite density or having time evolution. So in those areas, in principle, we still have a long way to go to learn many, many things. But I would be happy with the early steps. I think there's a lot we can learn precisely because we don't have to compete with the hugely successful classical endeavor that's already doing so well.
And by the time we get to something on the order of 20 to 40 qubits, you can't simulate it on supercomputers or your laptop anymore. So
yeah, that's right. 30 or 40 qubits is already at the limit. The question is, how interesting is the phenomenology at 30 to 40 qubits to an outsider? I don't know, but to me, it will be very.
Eduardo.
So there is I think distance in one dimension, but few decades. So, provided that the Montoni no highly successful density based which is closely related to things, but have you tried to do that? I think there you can do a very long system. But the problem of the non-local interaction, well, there has been for some systems with non-local.
So the question is, how well does DMRG compare to this that you've done?
Yes, I guess the attitude that people have often been taking here is that the one-dimensional system is not our final goal. We're really moving towards 3 dimensions. And so we haven't been focusing, or perhaps not yet focusing, on trying to do the best thing we can in 1 dimension. We're just imagining that we're building approaches that will scale to 3 dimensions.
But you're trying to compare, when they recap.
Yes. Okay, good point, good point. So you would say there are other good comparisons we can do. Yeah, yeah, absolutely. That's a really good point. Yeah, thanks for making that. Yes.
Yeah, please.
So, relatively connected with it. So, the system is something that sooner or later they will have. So you show some really nice or just sometimes scale of much larger what we can get with the interval or pretty long.
So the question is about thermalization in the system size.
If you're thinking about the curves Yeah. So this is just a four-state system that is being plotted as a function of time. This oscillation will just continue forever.
Yeah. Anything that they will still with time. That would make question. So
You're saying the height?
how you can do an with the amplitude that will decrease with the.
I guess it depends what you put on the vertical axis. I'm just not sure how to compare this, the height of the vertical axis on the plot that you have in mind. Yeah, this is Barry number down.
Oh, I mean, suppose that you can do an over one. Okay. So two operator induction will start to take. Because you will have probably the state that you are starting in the middle of the platform, so you will go in temper for humble. And
I think it's looking at another thing.
but that's not a state. So it's doing with that. So you start with some non-equilibrium state, which is high density of energy, and it's a less of the work. So it's not doing the job.
Yeah, we've just chosen a certain
Okay.
state from the. Right.
Thank you, yeah.
If we have hardware versus sim, why do we do hardware?
Right. I guess what we want to do right now is learn how to use the actual hardware so that when we can get to scales where simulation will not be possible, we can be confident that we're doing this in the correct way. So I should mention that along the way today, I showed an example of how to handle this gauge theory in one dimension, but it's certainly not the only thing that people are trying. This notion of rewriting the gauge fields as long-range interactions among the quarks, that's something that won't scale beyond one dimension. It's not something we can rely on into the future. And many other people are trying many other ways. So simulators are great right now as we're learning and testing, but we do also need to know about hardware so that we can go beyond the reach of any simulator. Yeah, nice.
Also add to that in looking at your papers, you seem to usually find pretty good agreement between sim noise and actual device noise. I've found the other sometimes. So how well the noise models work seems to be variable right now. So. Any other questions? Yeah.
So looking for that.
You're asking about self-mitigation. Are we looking for a systematic error? In a sense, I guess you could call it that. We're saying that the C0 gate, for example, supplied by IBM with the hardware, has a certain fidelity and it will make mistakes a certain amount of time. And we need to know as much as we can how often it makes those errors, what the consequence of those errors are. And our approach is simply to measure that phenomenon and then take that into account as we use those gates on those qubits.
So you come up with some error correction sequence.
Yeah. So in fact, just to make your point, when we run the mitigation circuit and separately we run the physics circuit, we actually run those in the same job, right beside each other at as close to the same moment in time as we can. So we run, because of randomized compiling, we need, say, 300 jobs of the physics circuit and 300 jobs of the mitigation circuit. We run one mitigation job and then one physics job and then one mitigation job and then one physics job, because you want to match the errors at that moment in time as best you possibly can. So you really want it to be two runs as similar as you can make.
Question, and then we'll head to lunch, please.
Mitigations you might be pushing right.
I don't have anything systematic that I can say, but definitely this is one example of mitigation. We've been happy with how it works, but there are many, many things that should all be combined as best we possibly can. Absolutely.